Welcome back to Mitch Tape. My name is Mitch, this is Pablo, and this is the first in a series of short educational videos on how Bitcoin works. Make sure you watch my What is Bitcoin video first, because it gives a very basic overview that we'll be drawing on throughout this series. Let's get going. The crypto in cryptocurrencies is short for cryptography, which is the study of secure communication techniques that only allow the sender and the recipient of a message to view its contents. Several types of cryptography are used by Bitcoin, but this video is going to be about hash functions, where a specific algorithm is used to transform data into a fixed length sequence of numbers and letters called a hash value, or just hash, which might look something like this. The first use of hash functions was for detecting accidental changes to raw data. Imagine you're sending a massive data file to a colleague and want to make sure that the file she receives is accurate. You can run the whole file through a hash function and attach the hash to the email, along with the data file. Your colleague takes the data file, runs it through the same hash function, and compares your hash to her hash. If they're identical, then the data is correct. So from this example, we can see that one of the features necessary in any hash function is that it's deterministic. That is, it doesn't matter how many times you repeat the process of hashing the original data, the resulting hash is always the same. On this visual, I've run the same data, Mitch Tape, through the same hash function on 4 different websites, and the hash is identical in each one. This makes a hash a sort of digital fingerprint, and if they didn't work like this, then your colleague's hash would never match your hash, and the whole process would be pointless. The second feature we need here is quick computation. It's much better for everyone if it only takes your colleague 1 second to hash the data, rather than 1 day, making the system much more efficient. The third feature of a hash function is that you can't reverse engineer the original data from the hash itself. This is called Preimage Resistance. The preimage is just the data which is being fed into the hash function, Mitch Tape in the example on the left. And resistance means it's infeasibly difficult to take a hash and figure out what its preimage was. Suppose the data you're sending is top secret, so you take the extra step of putting a password on the file and attach the hash of the data like before. If a competitor could take the hash and reverse engineer the data, it would again make the password useless. This leads us to the fourth feature of hash function. Any small change to the preimage should significantly change the resulting hash. In fact, changing just one character of the data going in is enough to change roughly 50% of the hash which comes out. In this example, our original preimage has an uppercase T. The new preimage has a lowercase t, creating a completely different hash and vastly improving the security of the hash function. Now, as I mentioned at the start, hashing algorithms transform any preimage into a fixed length sequence. Let's say it's 64 characters long. The preimage could be a single number, or it could be your favorite music album, or it could be every line of computer code that's ever been written. The hash function will always spit out a 64 character long string of numbers and letters. In this visual, 2 preimages of completely different length produce hashes of the same length. This means that whilst we have an infinite number of potential preimages, any piece of data you could possibly think of, when we put it through a hash function, it must be output as a standard length string of numbers and letters, which therefore has a finite number of potential combinations. This means it's inevitable that 2 or more different preimages will result in the same hash, because we have infinite inputs versus finite outputs, and this is known as a collision. This is the final feature of a hash function. It needs to be as collision resistant as possible. The harder collisions are to find, the more secure the hash function is. We could sum all of this up by saying the same input always produces the same hash, a slight variation to the input will produce a very different hash, but hashes will always be the same character length, and brute force trial and error is the only way to find a preimage that gives a certain hash. The most common hash function Bitcoin uses is SHA-256, which is the one I used for the graphics you just saw. SHA stands for Secure Hashing Algorithm, and 256 refers to the number of bits produced as output, which corresponds to 64 numbers or letters. Now, in the same way that computers use zeros and ones as part of a binary number system, the SHA-256 algorithm outputs numbers from 0 to 9 and letters from A to F, a choice of 16 characters in total. This is known as a hexadecimal number system. Hex comes from the Greek for 6. These factors make SHA-256 extremely collision resistant. In total, there are 2 to the power 256 combinations, or a 1 with nearly 80 zeros after it. That's our number of potential outputs, versus the infinite inputs just mentioned. This makes it very collision resistant. Hashing and the SHA-256 algorithm is going to crop up a lot as we make our way through this series. It's used very simply in the creation of public Bitcoin addresses. It's used in a way you wouldn't really expect in the proof of work process. And in fact, the history of the whole blockchain is secured by SHA-256 because each block features a hash of the previous block, which features a hash of the previous block, and so on. If someone tries to hash anything, anyone verifying the hash of the modified data will notice. Thanks for watching. Please comment, like, subscribe, and join me in the next one where we'll be looking at public key cryptography.